infinite bus. So what is this infinite bus? So when there is a load, a certain load, let us say this can be supplied by a single generator. So that means in order to supply this load, a single generator is enough. Let us say the load is increasing. Then we can connect more generators in parallel, right? Okay, further increasing, then again another generator, and so on. We can increase the number of generators, right? Now let us say the load has become so huge that there are so many number of generators. Then what will happen? The voltage and the frequency are not going to change with respect to real and reactive powers. Okay, so that is what we call as the infinite bus. So first write down the definition of infinite bus. An infinite bus is a power system so large that its terminal voltage and frequency do not vary irrespective of how much real and reactive power is drawn from or supplied to it. So that means if you plot the frequency versus power graph, this is the frequency and this is the power, real power that is delivered, let's say. Then what will be the graph? It will be just a straight line. So that means irrespective of the power delivered, the frequency is remaining same. Okay. So remember, this is the characteristic of infinite bus. Infinite bus is the collective, this entire large system that we have, that entire thing we call it as infinite bus. Okay. Now if you want to parallel a generator to this infinite bus, okay, if you want to connect a additional generator to this already existing infinite bus, then what will happen? If you plot the characteristics on the common axis, so that means this is the frequency, this is power, this is also power. Remember, we are not talking about negative power here. This is one plot, this is plot of the infinite bus, and this side we are drawing the plot of the generator. Okay, so that's what we are doing. This is the characteristic of infinite bus. Now, what is the characteristic of a single generator? It will be drooping. That means as power increases, the frequency will slightly fall. So now what we want is, we want the characteristic to be slightly higher. The no load frequency should be slightly higher than the system frequency. Okay, we've already discussed this point before. Now we will understand why that is the case. The paralleling procedure is the same. Okay, how are we going to connect a generator in parallel to another generator? We discussed the 3-lamp method, synchroscope and everything. The method is going to be the same even when we connect a generator to the infinite bus. So once we complete the paralleling procedure, what will be the operating point? This is going to be the operating point. Okay, because the system frequency is not going to change. The frequency of the generator, it will now be at this point, and at this point what will be the power? It will deliver that amount of power. So this power that we have here, this is very small quantity. Okay, so initially it will deliver only that amount. Using governor control, we can increase the amount of real power that is delivered. So we will discuss that as well. For now, you have to understand this point, that the generator, the no load generator frequency should be slightly higher. Now what will happen if it is slightly lower? In that case, you can draw a rough diagram here. This is the frequency, let us say, and this is the system frequency, infinite bus frequency. Now if the no load frequency is like this, slightly smaller than the system frequency, then what will happen? The only point that it is going to intersect is at a negative value. Okay, so remember, for this generator, this axis is negative side. For infinite bus, this is positive. Okay, but for the generator, the plot generator that we are doing here, the other side of the axis will be a negative value. So when the frequency, the no load frequency is lesser than the system frequency, then the generator will come into the parallel operation while consuming real power. Okay, so it will start acting like a load instead of acting like a generator. So this is what we want to avoid. That is why we want the no load frequency to be slightly higher than the frequency, system frequency that we want to set at. So you can write down this point here. When the incoming generator's no load frequency is less than system frequency, it consumes electric power and it acts as a load or runs as a motor. Okay, in order to ensure that the generator comes online supplying power instead of consuming it, that the frequency should be slightly higher than this, that the no load frequency, okay, should be slightly higher than that of the infinite bus frequency. So this is what we see right after paralleling. Okay, so in this situation, the incoming generator, the generator whichever we have connected to the infinite bus, it is said to be floating on the line. Okay, the reason is it is supplying a very small amount of real power. So you can write this down. The generator after paralleling is said to be floating on the line, supplying a small amount of real power. So now what we do is we make use of the governor control to increase the no load frequency. We can increase the set point. Okay, so what will happen if we slightly increase? The plot will be same, only it will merely be shifted up. Okay, so now what will happen at the same frequency? You can see now we have more amount of real power. Further, if you increase, once again you are going to have more power that is delivered. Okay, so in this manner, at whatever value of power we wanted to deliver, we can accordingly increase the governor no load set point. Okay, the governor set point is increased to increase the no load frequency. Now, since the system frequency remains same, since the system frequency remains unchanged, the power supplied by the generator increases. So we have seen how to control the power that is delivered, the real power. Now what about the reactive power? How to control the reactive power? This is controlled by controlling the field current. To control reactive power delivered, what we control is the field current. Field current is controlled. So how does this work? Since this is an infinite bus, the frequency is remaining constant, so the real power is remaining constant. Okay. So now when you draw the phasor diagram, terminal voltage, this also remains constant in infinite bus. What else is constant? The real power is now constant. That means at the particular system frequency, it is remaining same. Unless until we change the governor control, we are not going to change the real power for a particular governor set point. Okay. Now we know that the real power P, this is proportional to the armature current into the power factor. Okay. And also it is also proportional to the no load generated voltage into sine delta. What is delta here? It is the angle between no load generated voltage and terminal voltage. So where will be the phasor EG? If we have the armature current like this, then perpendicular to the armature current, we have the drop across the reactance. So it is going to be JIAXS. So now the EG phasor is going to be like this. Okay. So if this is EG, then what is this angle? This is delta. And this angle is phi. Okay. So now what is this EG sine delta and IA cos phi? This vertical line here. Okay. So this is EG sine delta. So that means this is going to be proportional to the real power. Okay. Also, what is IA cos phi? It is this distance. Okay. Once again, the power is proportional to IA cos phi. So we are representing this because the power is remaining constant. So now when we control the field current, how the reactive power is increasing while keeping these values here constant. Okay. So when we increase the field current is increased, implies that the field flux is going to increase. So what will happen to the generated voltage? This is proportional to the flux phi and the speed. Now the speed is remaining constant because the frequency is constant. So what will happen to EG? It is going to increase because the flux is increasing. Okay. Now EG has to increase in such a way that this EG sine delta, this is remaining constant. So how does that happen? The phasor can only slide on this line. Okay. So that means if you draw a line here, EG can slide anywhere along this line. Okay. So you can take them as EG1, EG2, EG3. Okay. Now what is the effect of this increase in? If you increase field current, the phasor will move this side. If you decrease field current, it will move this side. Okay. Now what is the effect of this? The phasor that is changing is the drop across the reactance. Okay. So it can slide along this line once again. Now when this is increasing, what is the result of this? The armature current is going to vary, but IA cos phi should remain same. So the armature current should vary, maintaining this particular value to be same. So how does that happen? Once again, you can draw a line here. So the phasor should start from here and it should slide along this line. Okay. So if you take this phasor EG2, IA axis here is perpendicular to this IA. Now if we have increased the field current, EG is increasing and IA axis is moving to this side. So what will happen to the armature current? This will also rotate in the clockwise direction. IA axis has rotated in the clockwise direction. So IA also will move in the clockwise direction by the same angle. Okay. The final result is that this vector now, phasor now, it should be perpendicular to the new armature current. Okay. So we are going to have something like this. So this is IA2, this is going to be IA3. So what else is happening here? You can also see that the power factor angle is also increasing. Okay. So now this angle is, this is phi 2, then this is phi 3. Okay. Now what is the reactive power? It is proportional to IA sin phi. Real power is proportional to IA cos phi and reactive power is proportional to IA sin phi. So what is IA sin phi? It is going to be this drop. Okay. So this is IA cos phi and this is going to be proportional to the reactive power. And you can see that this is increasing. Initially it was only this. As you increase the field current, reactive power has increased. Okay. So this is Q2, let us say, and this is Q3. Okay. So this is how increasing or varying the field current will be used to vary the reactive power. So you can write down here, when you are increasing field current, flux is increasing, the generated voltage is increasing. Since terminal voltage remains constant in infinite bus and the power is also remaining constant. Power is the same for a particular governor set point. The no load generated voltage should increase in such a way that Eg sin delta remains same. Why is that? Since the power is proportional to Eg sin delta. Okay. And the only way this happens, Vt is also remaining constant, Eg sin delta is also remaining constant. So the only way it is happening is by sliding along this line. Okay. So as a result of this, drop across reactance varies as shown in phasor diagram. Consequently, the armature current must change, but with the constraint of IA cos phi remaining same. Once again, why is that? Since P is proportional to IA cos phi. So IA varies as shown in phasor diagram. So the reactive power Q, which is proportional to IA sin phi, will vary accordingly. Okay. So what is the final result? Therefore, as the field current IF increases, the reactive power Q is also increasing. Okay, so this is how you control the reactive power. So the three things that you should keep in mind for an infinite bus are, the very first point is that the voltage and frequency remain same. Second is the real power is controlled by governor control. The reactive power is controlled by field control. Okay. So these are the points that you have to remember for the infinite bus.